we mentioned that the sample average x bar is we are averaging for each one of the possible value of x, how many times it appears in x, and then divide by 1 over n, the number of samples. If you think about this value of number of times it appears divided by total number of samples, that's nothing but our estimation of the probability that it appears in the huge set, in the full population. So it's just like writing x times the probability of x. And that would be our estimated of the average. And we'll see without a proof two very fundamental results that said one, that as large as we are increasing our sample to be larger and larger, of course, and a lot of miracles happen, like that all the variables are all independent of each other, and a lot of nice things happen. The law of large number says that the sampled average tends to be very close to the real average, the real mean of the whole population. Actually, there are results that Chernoff bound that said that the probability that it's far away from the average, that our sample is far away from the average, the probability that this happens decreases exponentially with the size of our sample from the population. That's called Chernoff bound. Other theorem said that for any different values that we are measuring, of course, if we are taking different samples of the same population, we are getting different sampled means, obviously, each time we are sampling different peoples. However, how are these different means tends to look like? They are going to look like a normal distribution. Very unlikely in this aspect, and it follows the Gaussian distribution, very unlikely to be far away from the overall population. Okay, sample means, once again, if n of 1 is the number of times that 1 appeared, see the marker here, yeah, if n of 1 is the number of times 1 appeared, n of 2 is the number of times 2 appears, it's not n times 2, it's n of 2, then the average of this set is just takes the individual value, each one with the number that it appears, n of I, that's the total sum, and here is the average of this number. Not so popular. So you can also think about it as n of x as a frequency of x in the overall population, and sum up these frequencies and normalize it by the total number of sample points. So it's just like taking the x times p of x. Worth mentioning, sometimes we want to take the weighted average. Somebody gives me weights, and these weights, wi, are what we call convex combination. The weights, each one, they sum up. They are between 0 and 1, and they all sum up to 100%, to 1. Sigma of wi is 1, and all the weights are positive. Example, your overall grade would be, say, it's not a real number, but just an example, 20% of the midterms, that's the weight of the midterm, the weight of the final, and the weight of other factors, and that would be weighted average of your overall grade. Why do we want weighted average instead of the real average? Well, sometimes we want to increase the rule or the effect of one of the samples versus other samples. Okay. Next, that's pretty important factor. So I we sampled values xi's from the real population. We just know we can just estimate some parameters of the real population, but we never sample enough many people to be absolutely certain. However, we have this value x star, and now we ask what is the spread of this, how far away values tends to be from the average. What's the average distance from the mean, from our sampled mean? How come it's sampled mean? Because we don't know what is the real mean. So what is the average distance? And as usual, we had this discussion before. We don't, had we just sampled these values without a square, some values are positive, xi is smaller than the mean, some values are larger than the mean, so they'll cancel all each other by definition of the mean. So we can take either the average distance as an absolute value of this distance, or take care of the square of the distance, make sure that they are all positive, and next takes the average such distance. And to get our estimated about a standard deviation, we'll actually take the square root of this number. But let's just call it sigma, our estimation. And you see that that already suggests some cascading of errors, because what are we assuming? We are measuring the standard deviation on our sample point, and it uses already this value that might contain error already. However, that's kind of the best that we can do, except that if we do the obvious 1 over n times this average distance, we'll see that it tends to be biased, it tends to overshoot. And we can fix it by taking not 1 over n, but 1 over n minus 1, which will be less accurate, but unbiased. It sometimes hits above, sometimes hits below. Okay, so quite important, giving us a lot of the information about the spread of the information. We know the average. Now we know the average. Now we are asking how likely it is to find a value which is far away from the average, at least the sampled average. Okay, let's mention another term that you are probably familiar with, the quartile. The first quartile will be the lowest 25% of the data. Second quartile would be the lowest 50% of the data. That is, we're asking here what is the value that had we sort all the data, that would be in index. If we sort the values x1 smaller or equal than x2, smaller or equal than x3, smaller or equal than xn, then the first quartile would be n would be x of n over 4. Second quartile would be x of n half. And half, remember, there is some nuances here. If n is even, then we're taking the average of the two n half and n half plus 1. Third quartile will be x of 0.75 times n, of course, floor or ceiling of this value. And the fourth quartile is just a maximum. Doesn't be really useful, or at least doesn't give us any more information more than the quartile, more than the just knowing the maximum. These properties are quite obvious. We can ask NumPy to compute it for us in a vector x of all the values. Ask what are the 0.25, 0.5, and 0.75 of the quartile, and NumPy will be happy to compute it for us for actually any value of quartile, as you see. We can also ask to visualize this using a box plot, where in the box plot we'll write what is a minimum, what is a maximum, and then we'll ask what is a first quartile and the third quartile. Why this box is so important? Because it's pretty robust. It tells us a lot about the distribution of the data. However, it's not really affected if somebody suddenly have an enormous value. Doesn't affect the median and doesn't affect the fourth quartile at all. So we'll tend to think about it as these box that contains always, by definition, 50% of the data. This box is, in a sense, a real distribution. Tell us these 50%, how small or large they are distributed around the median. And in addition, we will tend to think about the lowest 25% and the highest 25% as kind of outliers, maybe less representative, less important to know about the overall data. And of course, these values over here and over here affect the average, but do not affect these median and the center to quartiles distribution. So that's box plot, and if you want to, how algorithmically we can compute it by either sort and use these indices that I just mentioned, or we can think about take the median of the whole set, look at all the values that are smaller than the median, and now find among the smaller values, the smaller 50%, their median, and repeat it for the largest 50% of the data, which suggests actually some algorithmic advantage, because sorting takes n log n, while finding the median you can find very, very easily in linear time. If you take algorithms with me, I'll show you how. Okay, and maybe we want to see it visually, for which we can ask for a box plot of the data. And box plot of the data. And just to introduce one more library, scientific Python, SciPy, large library that suggests more statistical oriented functionality, more statistically serious operation of on data, like if we like computing the norm, but also asking for computing all the moments. We talked about mean and standard deviation, but we can ask about similar statistics. That is quite important. And we can even trim pieces of the data that are not relevant and do other machine learning operations that at the moment not necessary to discuss right now. Okay, let's mention in this context also a Anscombe quartile that is copied here. Check which is relevant, because you can play with this by reading the CVS of Anscombe, and what this is type of data sets that people like to bring. Sorry, so did I update it? Yeah. Check the Wikipedia about it. So what's interesting about this data set is that there are actually 4 data sets in this file, and all the statistical parameters of the data set are the same, but it just shows but the actual data is very, very different. Again, the statistical parameter, average, standard deviation, all the same, very different data sets, kind of demonstrating the short sense of the statistical parameters by themselves without looking at the real data. And people, of course, like this behavior of let's play with different data sets that have same statistics. So it goes much further. A lot of data sets all have the same statistics, but very, very different than each other. So take the statistical parameter with grain and salt. That's the message from it. Taking a break.